So now, as I told in the beginning, we are going to study all these with respect to MOSFET, because our goal is we are going to use MOSFET everywhere. Throughout the subject, we are going to use only with MOSFET. We are not going to use conventional BJTs. So having known about what is flicker noise, we will try to narrow down and see where is flicker noise present in MOSFET, because we are more bothered about that. We have seen thermal noise is present in drain current. We have seen thermal noise is present in the gate terminal in the with respect to MOSFET. So same way here we are going to see where is flicker noise present in MOSFET. So MOSFET will have a higher amount of flicker noise when compared to BJTs, when compared to BJTs. Okay, so one means of comparison is to specify a corner frequency where the noises are equal. So you can find a frequency where these two noise components are going to be equal. So all other things are held equal. A lower 1 by f corner noise implies less total noise. The total noise is going to be sum of all the noises. The corner frequency means you are finding a particular frequency where all these noise components are equal. The magnitude is equal. So even if one is going to be larger, the effective noise will be larger. So I'm going to find an optimal frequency where all these components are equal. So if that frequency is going to be lower, I can say that noise is also going to be less. So they have done this experiment in MOSFET and they found that this corner frequency is tens of kilohertz to megahertz. So in between, in the range of tens of kilohertz to megahertz, relatively all the components of noise are equal, and when you average out noise, it is going to be a minimal quantity. So the effect of noise is going to be literally minimal. Okay, that is what is meant by the corner frequency. So in MOSFET, we have one, in transistor generally, we have this charge trapping phenomena, which is usually the cause of 1 by f noise. We have seen in short noise, the random arrival of electrons will contribute to short noise, right? So same way in transistors, we have this charge trapping phenomena. You have three regions: emitter, base, and collector. If you're going to see MOSFET, you have source, drain, and gate, right? So definitely you have charge carriers in each of these regions. And definitely when you are going to apply an electric field across a junction, some charges will get influenced and start moving. Some charges are still trapped in the region itself. So these trapped charges will give rise to what is called as 1 by f noise. Also, while manufacturing, you might have defect. Some impurity might come into your atom because of doping. So that can randomly trap and release your charges. So this trapping and releasing of charges randomly is going to be the major cause of flicker noise in MOSFET. And when it is going to trap, when it is going to release, everything is random. So since it is going to be completely random in nature, so the trapping time and the releasing time in a MOSFET will lead to 1 by f noise dominating in a larger fashion. And you know, MOSFETs are surface devices. They are fabricated in the surface wave technology. So they exhibit this noise to a much greater degree than the bipolar transistor. You know, MOSFETs operate by, oh, I'm going to apply voltage to the gate source terminal, and I'm going to induce the current flow into my channel. So MOSFET is a voltage controlled device. So I'm going to apply electric field. This electric field will give rise to charge trapping and releasing phenomena more frequently when compared to BJT. That's why we say that flicker noise is more in MOSFET when you compare with bipolar transistors.